forms of energy. We call these things different forms of energy, different hidden ways of calculating the number of blocks. However, I want to amuse us today by discussing the formula for gravitational energy around on the surface of the Earth here, not going very far away. And I want to derive this formula in a way that has nothing to do with history. It's simply a set of reasoning which I have invented for this particular lecture. And it's patterned after a very excellent argument by Mr. Carnot on the efficiency of steam engines, but it's applied here to calculate or to understand the law of how to calculate the energy and what the conservation of energy is in the case of gravitational energy. So what I want you to do is to consider weightlifting machines. That is a machine which has this property that you put a weight here, it lifts another weight while lowering some other. I want also to make an hypothesis, which is that there's no such a thing as perpetual motion with these weightlifting machines. In fact, that there's no perpetual motion at all is a general statement of the conservation of energy law. I must be careful to define perpetual motion. First, let's apply it to weightlifting machines. If you've lifted and lowered a lot of weights, take the weights off, you can restore them and restore the machine to the original condition. And find when you're all finished that the net result is to have lifted a weight, then you have a perpetual motion machine because you can use that lifted weight to run something else, provided that the machine which lifted the weight is brought back to exactly the same condition as it was before. Furthermore, that it's completely self-contained, that it hasn't received the energy to lift that weight from some external, but Bruce's blocks haven't been thrown in. Now I have a very simple weightlifting machine here. Here's a machine for lifting weights 3 units strong, which I put on this panel. By placing a weight on this panel, in order to get the thing to work right, however, I'll explain about this. You have to lift this little thing. Now, we just don't worry about that, but that lifts this. That lifts this. On the other hand, I could lift the 1 unit weight by lowering the 3 unit weight, provided I cheat a little bit by lifting the one on this side. I want you to realize in any actual lifting machine, I have to add a little extra to get it to run. Please disregard that temporarily. The ideal machines won't require that. They don't exist, and we'll come back and discuss that little business, that in order to make it work, I have to move this. The machine that I have here is, in the sense, almost reversible. That is, if it'll lift the weight of 3 by lowering a weight of 1, then it will also lift the weight of 1 the same amount by lowering the 3 the same amount. Nearly. So we imagine that there are 2 classes of machines, those which are not reversible. This is really not reversible because I have to fiddle around with these little extra weights. But we have a machine, so a general machine is not reversible. In fact, any real machine is not precisely reversible. But as we improve the fulcrum and the levers and so on, we find that the amount of stuff that has to be lifted gets weaker and weaker. And so, with our imagination, we idealize to the possible existence of a reversible weightlifting machine. So suppose that there was such a thing. Suppose now that I have a reversible machine which does this. A 1 unit weight, let's say a pound or any other marker for the unit. 1 unit weight is lowered by 1 foot, say, or any other unit of distance, doesn't make any difference. And when this happens, the machine lifts a weight 3 units, say, as this one does. And that's all the machines I'm going to consider now, all the various devices. This is the simplest possible one. I get screws and axles, inclined planes, and all kinds of levers and machinery can be inside, but the net result of the machine that I want to discuss is that it takes a 1 pound weight, lowers it 1 foot, and in doing so, lifts a 3 pound weight some distance. Now let's suppose that we have machine A and this reversible machine. And this particular reversible machine lifts the 3 pounds a distance x. And now I have another machine, a machine B, which is not necessarily reversible, is not reversible, or is, whichever you want, is or is not important. Let's say it isn't for the sake of argument. It lifts 3, a distance y. Now what I'm going to prove is that y is not higher than x. That it is impossible to build a machine that will lift a weight any higher than will be lifted by a reversible machine. Let's see why. Well, let's suppose that y were higher than x. I don't have to draw pictures, I can wave my arms. Look. You take a weight, 1, and you lower it 1 foot with the machine B, and that lifts the weight 3 up a distance y. Now you lower that. See, if y is greater, I'm going to prove, or let's say what I'm going to prove. Y is not higher than x. Suppose it were. Then I've lifted the weight higher than I need. Then x, the distance, say y is up here. And suppose x is only this high. Then I can lower the weight from y to x, obtaining free energy, free power. And then use the reversible machine A running backwards, which according to this will lower a 3-pound weight, x, and lift the 1-pound weight 1 foot, which will put the 1-pound weight back where it was before, and I'm ready to use machine B again. In other words, I lift with machine B by lowering the weight 1 pound, I lift the thing 3 pounds up y. Then I lower it a distance x and get my 1-pound weight back before. But since x is less than y, I have a little bit left to go. I can make the thing do something when it's fall between y and x. And therefore I have perpetual motion. So if y were higher than x, I would have perpetual motion, which I assumed was impossible. So therefore, with those assumptions, I deduced that y is not higher than x. Therefore, of all machines that can be designed, the reversible machine is the best. No matter how you figure out with the wheels and the gears, you better try to make it reversible. Now I'll show you something else. All reversible machines must lift at exactly the same height. Because suppose that B were really reversible also. Well, the argument that B is reversible, that y is not higher than x, is of course just as good as it was before. So y is not higher than x. B is now reversible, however. And I could make my argument the other way around. You stop and think a minute, you'll see what I mean. I could make the machines run in the opposite order. So I could just interchange the B and A in the argument. And I can easily prove the other thing, that x is not higher than y. In other words, if I had 2 reversible machines and one lifted higher than the other, then I can use that extra difference and then make one run the other backwards to keep the cycle going. So therefore, if I have a reversible machine, all reversible machines lift the same distance, no matter how they're constructed. If they drop 1 pound, 1 foot, and lift 3 pounds, the same distance, no matter how they're constructed. This then is a very remarkable observation because it permits us to analyze the heights at which different machines are going to lift something without looking at the interior mechanism. And we know right away that if somebody has concocted a series of levers that's enormously elaborate, that lifts this a certain distance, and I compare it to a simple lever like this, which is a fundamentally reversible, I know this is going to lift it no less high. I know exactly how high it's going to lift, and I know that it's no use trying to redesign the machine to get greater height. So you see that this x is a very important general proposition for all machines. To summarize, every reversible machine, no matter what, or no matter how it operates, which drops 1 pound by 1 foot and lifts a 3-pound weight, always lifts at the same distance x, irrespective of the machine, and therefore something in great generality, It's a universal law of great utility. The next question is, of course, what's x? After all, it's an interesting law to discover because it's the same for all machines and doesn't depend on any particular one, so I can get the x that way. One way is to invent a reversible machine and figure out how high it lifts. But I have a more ingenious argument for you that tells us what x is, and so I'd entertain you by the following argument. Suppose that we have a reversible machine which is going to lift this distance x, 3 for 1. I set up a set of 3 balls here. This is only a rack to hold the balls and it doesn't move. This ball is being held on a stay up here at a distance 1 foot above the ground. The machine lifts, if I put, this is the other part, this is the machine here. This is platform and this piece here.